We're going to talk about general relativity in this section and also touch a bit on special relativity. I sometimes think people don't really understand how important Einstein's discovery of general relativity was, but it was immensely important, and it's immensely important to some of the things we're going to talk about. There are several things that I want to emphasize about general relativity. The first thing is that space actually consists of time. So I don't want you to think of space anymore as simply X, Y, and Z axes. I want you to also think about it as having a time component. So think of it as space-time, because as we move through space, our clocks also are affected by that. Every time you walk down the hall, your clock is slowed down slightly by that process, infinitesimally small. But when you start getting up to the speeds of light, your clock can visibly slow down. So very important, and also extremely important is the impact that Einstein had on our notion of gravity. General relativity redefined the way we think about gravity. It didn't change Newton's equations of gravity. We still use them to get to the moon, but it's certainly a refined and certainly a different way of thinking about gravity, and that is that mass warps space-time. So if you look at this sheet here, you'll see what I'm talking about. We've got the Earth sitting on a rubber sheet, and it's forced that rubber sheet down into a well. And if a spaceship's traveling by and it gets close enough to the Earth, it's going to be drawn towards the Earth, not in a straight line, but in a curve. So that's the concept that we want to think about when we think about space-time. Take, for example, a bowling ball on a rubber sheet. If you put a bowling ball down, then we can kind of think of that rubber sheet as the bowling ball having a gravitational pull, and if you roll a marble across the rubber sheet and you get it close enough, even though the marble's going on a straight path, it'll be deflected by the depression caused by that bowling ball. It's the same thing with gravity. That's how I want you to think about gravity. It's really a warping of space-time, and you can see it visibly here, the way the Earth is affecting that. And it's given us a new idea, really, of what gravity is. A new concept, I should say. Well, whenever somebody proposes something in science, somebody else generally comes up with a way to test it. And this is a picture of Arthur Eddington. Eddington, after Einstein proposed general relativity in 1915, Eddington proposed a way to test it. Now, they couldn't test it during World War I. The war was going on, and so they had to wait until after the war. But Eddington proposed that he should go and look at an eclipse and see how stars were affected by our sun. The idea, as you can see in the diagram, is that when the moon goes in front of the sun, that you'll be able to see the stars behind the sun, and you'll be able to see how they're affected by the gravitational pull of the sun. They should be, if general relativity is correct, they should be warped or gravitationally lensed by the gravitational pull of the and that is precisely what Eddington found when he went to measure the position of stars behind the sun during the eclipse. What he did is he looked at the stars where the sun was going to be, then he looked at the sun when it was there, close to those stars, because he could see them as soon as the moon covered up the sun, and then he checked it again afterwards. Now, it's debatable whether Eddington's data was good enough to say that he had successfully tested general relativity or not, but subsequent experiments have definitely shown that general relativity, I should say, is correct. At least this experiment proves Einstein was right. Substantiates probably a better term than proves. Now, I need also to talk a little bit about special relativity. Some of the things about special relativity we're going to need to know for things we talk about later on in the course. So let's drop into special relativity, if you will, and talk a bit about that. Einstein came up with special relativity before he came up with general relativity, and several things to keep in mind, and that is that the first thing is that light in a vacuum is a constant. And the second thing is nothing can travel faster than the speed of light. So it's sort of the upper limit of how fast we can travel. And we know this because as you start to approach the speed of light, your mass starts to go to infinity. And if you're at the speed of light, your mass will be at infinity. It would take all the energy in the universe to propel you to, get you to, even another tenth of a percent towards the speed of light at some stage. So regardless of what you hear in Star Trek and science fiction, it looks like that's an upper limit to us in terms of being able to travel through space-time. Also, E equals mc squared. We've got to keep that in mind. That comes out of the relativity equations. We created atomic bombs because of E equals mc squared. So some bad things and good things can come out of this stuff. One of the experiments, one of the ideas that we have is that if we're traveling in the direction that the Earth is rotating and I flash a light out there, you would think, if you're just thinking about this, you would think that the speed that light is traveling is the speed plus the additional rotation that the Earth is moving. And yet we find that's not true. We can measure the speed of light in the direction the Earth is rotating, and we can measure it in the opposite direction against the rotation of the Earth, and we get absolutely no difference in the speed of light. So that means then that special relativity tells us that the speed of light is a constant, that it's going to travel at the same velocity no matter what you're doing. So everything's relative in that sense. Now, we want to focus on this cone of light just to see the implications of what special relativity is telling us here. We want to think of it as a future light cone. If I send out light from a flashlight, the only people that are going to be able to see that in the future are people that are in this future light cone. So anybody that's outside of that future light cone, in time or space, is not going to be able to see that light. And that also has implications for the past. If something happens and it's so far away from us that the light can't get to us right now, then we're not going to see it. And I'm going to talk about Euler in just a minute, but it has ramifications. And of course, there's some really weird stuff with special relativity. Weird stuff like time dilation. As you travel faster and faster, and you start to get fast enough to where you're at large percentages of the speed of light, your clock slows down. Now, I don't mean that your clock slows down like if you're carrying a clock and your clock slows down. I mean you actually look to someone that's observing like you're moving in slow motion. The clock is slowing down, you're slowing down, and if you looked at someone else, they would look like they were slowing down. So it's a very strange phenomenon, time dilation. There's also a length dilation. So if you're traveling at or near the speed of light, well, not at the speed of light, but if you're traveling near the speed of light, then there's a length contraction. So if I'm traveling near the speed of light in this direction, I'm going to get thinner in this direction. I'll lose a little weight. So there's that component too. And then there's this strange simultaneous things being removed. That is, we have no sense of what might be simultaneously happening. If I move my right hand and then my left hand, that's the way it may seem to me, but somebody traveling near the speed of light may see it and not in that order. So these are really bizarre ways to look at the universe, and yet every time we go out and we test these things, we find out that Einstein was right. So imagine thinking of this kind of stuff and then having people go out and run experiments to see if you're right. And one of the cool experiments that was done in the 1960s, they came up with cesium atomic clocks, and two guys named Haffel and Keating got in an airplane, took their cesium clock on an airplane, you can see a picture of it here, and they got on the airplane and they flew twice around the world, and they had a cesium clock that they left behind, and they started them at both the same time, took the two flights around the world, came back and matched the two clocks, and sure enough, the one that went on the flights had slowed down just the way they had anticipated. So it's quite amazing that you can get that kind of precision and test, but it's been tested many times in other ways, and every time it keeps coming up the same. Special relativity has been fairly well documented. Now, I want to go back to this issue of thinking about space-time and what general relativity kind of tells us about space-time. Space-time, because it's integrated and it's expanding, all the galaxies are moving away from us. You might think that we're in the center of the universe because everything's moving away from us. Well, I want to dissuade you of that idea. Because it doesn't matter where you are in the universe, everything will be seemingly moving away from you. Let's talk about a rubber sheet with some poker chips on it. If people were at each corner and we pulled it apart, all those poker chips would look like they're moving away from each other, which is exactly what is happening. But if you were on one of those poker chips, it would look like everything was moving away from you, and if you went to another one, that's the way it would look too. And another way to think about this is a balloon. If you could be converted to Flatlandville on the surface of a balloon where there are only 2 dimensions instead of our 3 dimensions. So forget about that 3rd dimension. It doesn't exist in this thinking about space-time expansion. If you blow up the ball and you're on the surface, that surface of the balloon, it has no edge and it has no center on it. And all of the little tiny marks on the balloons that look like galaxies are going to be moving away from you no matter which galaxy you're on. So that's the way to think about space-time expansion. Here now is a scary graph for some of you that are not used to math. So please go to sleep or go get something to drink during this if you're not interested in the math. I'm just throwing this up here for the people that are interested in seeing how some of these calculations are derived. What I'm interested in explaining to you is what AT is. So that's where I'm eventually headed, which is the cosmic scale factor. But I'm going to start out with giving you an equation for redshift, which is Z here. We talked earlier about redshift. You know we can get velocities from redshifts. I never told you exactly how. But Z, if you remember that wavelength, one of those, it doesn't matter which wavelength, as long as it's the same wavelength, but the wavelength of one of those spectral lines that's missing, you can take that wavelength and you can subtract the wavelength of a stationary body like the sun from it, and then you can divide by that same stationary wavelength. That would be the difference, that is the shift of the redshift of that particular wavelength. And that gives us C. And Z, if you use the equations for general relativity, Z is approximately equal to velocity over the speed of light. And then we can derive from this the Hubble law. And the Hubble law comes from that graph that you may remember, velocity versus, or I should say distance versus velocity of the galaxies. Remember, whereas distance increases, the velocity of the galaxies moving away from us increases. Well, that is the Hubble law. That's right here. That's what gives us those velocities. And it's a constant here right now, and that constant's been calculated rather carefully. It's at 67.80 plus or minus 0.77. The guys that recently calculated that, and it's just been done recently, they won a Nobel Prize for it, and it's given us the age of the universe. So when I was quoting you the age of the universe, it comes from the equations that we use the Hubble constant in. So very, very important number. Now, before I go on, there's something I have to tell you, and this is something we have to consider. When you think about space expanding, remember that it's also going to expand the wavelengths as they travel towards us. So there's going to be a built-in sort of redshift from the expansion of space. And when you get out far enough into space, you're going to have to start considering that, because it's going to make it look like that star's traveling faster away from you than it really is, because there's that extra red shift from the wave traveling through space as it's expanding, if that makes sense. So that AT value is going to help to show us how the red shift affects that. And that's why I'm trying to get to this AT value. AT is the cosmic scale factor. And AT is equal to 1 over 1 plus c. That's all you need to know. Not complex. It's a little harder to derive from the equations of general relativity. Certainly don't want to get into it here. But I did want to explain it to you mathematically, because we're going to talk a lot about it when we start talking about whether or not space-time is expanding and what the speed it's expanding is. In other words, we're going to find out that space-time is accelerating, and that's what won the guys the Nobel Prize recently. So that's going to be important to talk about, and we need this AT value to talk about that. If the red shift is 0.5, then AT is going to come out to be 2/3, which basically means that the universe, when that star formed and sent that light to us, was 2/3 of the size it is now. So that AT is going to be very valuable in looking at the expansion of the universe. So don't freak on the equations, pretty simple. I do want you to keep one thing in mind, and that is that the cosmic scale factor is important, because once you get out past about 10% back out in the age of the universe, then you have to start worrying about this red shift from the expansion of space. The light's going to be traveling long enough to where it's going to be affected by that expansion of space, and that's going to mess up our calculations of distance if we don't consider it. So it's cosmic scale factor, very important. Okay, so I want to go on and talk a little bit about quasars. Quasars are quasi-stellar. That's what they stand for. And we didn't know what they were. We still don't completely know what they are. But it looks like that they are super gigantic galaxies that are being sucked into super black holes out in space, and they're about 100 times more bright than our galaxy. So they're immensely bright things, and we can see them for long distances. So they're the brightest objects that we see out in space. And here's a graph showing you, and oddly enough, nobody knows why, but during an early period in the universe, we had an immense number of quasars formed. Again, one of those mysteries that is keeping all those astronomers with jobs. There's one more thing I need to cover in this section, and that is Eulers Paradox. Way back, a long time ago, I think it was the 1600s, Euler asked the question, why is the night sky dark? And it's really a good question if you think about it. If there are an infinite number of stars out there in our sky, then the night sky should be bright as day. So what's going on there? Why don't we have a bright sky? Well, we're lucky we don't have a bright sky, because if we had a bright sky, we'd all be burned up. No life could ever exist here, because there would be so much energy coming from the Earth. But we think the reason is because, and we can now explain it, it's because space is expanding and that some light hasn't reached us yet. It's the cone of light that I talked about earlier. If an object is outside of the past light cone, then we're not going to be able to see it now. That means its light hasn't reached us. This diagram on the left is probably a better diagram to look at. You've got a star here that's 8 billion years old, and it's 7 billion light years away from Earth. Well, that means that its light has reached us because it's been around long enough for its light to have traveled to us. But now down here in the other one, you've got a star that's 4 billion years old, and it's 5 billion light years away from Earth. Well, its light hasn't reached us yet. So we will not see that star. Now, one thing that's going to become clear from this is that the night sky should, as time goes on, gradually get brighter and brighter, because we're going to start seeing a lot of stars that we can't see now. But because space is expanding, it's going to negate some of that too, so don't worry about burning them tomorrow, that's for sure. Let's just conclude then with this number, 13.798 plus or minus 0.037 billion years old. That's how old the universe is. I could not have told you that number 12 years ago, 10 years ago, whatever, because it's just been discovered. We just came up with the whole Hubble constant. All this is new and exciting. I mean, we can stand here today and I can tell you how old the universe is. That's an amazing thought when you think about it. Approximately, if you want, 13.8 billion years ago, the Big Bang occurred. Now, we don't know exactly what the Big Bang is. Science is always going to tell you they don't know when they don't know, and we don't know. More about that later on. I do want to make sure that you also get this concept from this slide, and that is the observable universe. Because when we look out into space, we look back in time, as I've mentioned before. So that means that everything that we're seeing is very old. And the farther out in space, the older. And that means that the universe has gone on and expanded to where now our universe, what we call the observable universe, because we can see those things back in time, all those things we're seeing now, they've moved on. And so the universe is much bigger now than it was back then. And so the radius of the universe is believed to be 93 billion light years across. That's what we're talking about right now. Amazing number.